Okay, folks, so in the last video, we looked at the graphs of the exponential and logarithmic functions, and we also looked at the graphs of 2 to the x and log base 2 of x. So what I'd like to do now is, it's sometimes helpful to put several graphs together on one axis to help kind of see a little bit more about what's going on. So I'm going to go ahead and try my best to roughly sketch the graphs of 2 to the x, 3 to the x, and e to the x all on this first axis here. So let's go ahead and do the graph of f of x equals 2 to the x first, and I'll do that in this magenta pink color. So if we were to plug in 0, we know that anything to the 0th power is 1, and so the graph of 2 to the x, like all of my exponential functions, must initially pass through the ordered pair 0, 1 prior to transformations. Likewise, we know that if we plug in 1 into our exponential function, 2 to the x, f of 1 needs to output 2. And so I can now go ahead, let's do one more. If I plug in -1, it's going to spit out 1/2. And I put a little tick mark there. It's kind of hard to tell, but that tick mark right there is for the value 1/2. And so now I can go ahead and try my best to sketch the graph of 2 to the x. So here I've done my best to sketch the graph of 2 to the x. Notice that it has this horizontal asymptote here at y equals 0. Okay? So now let's go ahead and in blue, let's go ahead and look at the graph of g of x is equal to 3 to the x. So just like 2 to the x, 3 to the 0th power is 1, and so the graph of g of x must initially pass through the order pair 0, 1. And then if we were to evaluate g at x equals 1, we get out just the base of the exponential function, so we get out the order pair 3, 1. And then finally, if we were to plug in -1, let's just do that. If we were to look at g of -1, we get 3 to the -1 power, which is 1 over 3, so a third. And you don't know this here, but there's the order pair, or there's the x value, the height 1/3. And so that would be about this point right here. And again, I'll do my best to sketch the graph of this exponential function, 3 to the x right here. Okay. Now my point for doing this is because in a previous video I said a lot of times students struggle with graphing e to the x. And I want to point out that if you can sketch 2 to the x and you can sketch 3 to the x, then you can also sketch a graph of e to the x. So let's go ahead and do that. I'm running out of colors here, so I guess I'll go ahead and pick this gray color. Let's see if this works. Nope, that's not going to work. So let's pick this yellow color here, and let's look at h of x is equal to e to the x. So just like the other two exponential functions, anything to the 0th power, e to the 0th power is 1. And then e to the first power is just going to spit out the base. Well, remember that e is approximately 2.718, and so e to the first power is going to spit out a number close to 2.718. These should all be in a nice straight row here, folks. Let me scoot that over slightly. Those should all those dots should be in a nice straight row there. And now I can go ahead and sketch the graph of e to the x. And the graph of e to the x we see lies between the graph of 2 to the x and 3 to the x as we sketch it. So there we've got the graph of e to the x. I think it's really important to do this because it takes some of the mystery out of the exponential function e to the x. If you can sketch 2 to the x and you can sketch 3 to the x, then you can sketch e to the x. So now I'd like to do something similar. I'd like to sketch the graph of these, their corresponding inverse functions. So we'll first go ahead and sketch f inverse of x, which would be equal to the log base 2 of x. Now, this fact doesn't quite roll off the tongue. Remember, we can say that anything to the 0th power is 1. That's true for 3 to the 0th power, e to the 0th power, 2 to the 0th power. All of those gave me the output value of 1. But because of the domain range relationship between a function and its inverse, all of my logarithmic functions prior to transformations, this is what we said on a previous page, must pass through the ordered pair 1, 0. So for example, if we go to sketch the log base 2 of x, it has to pass through the order pair 1, 0. Similarly, because the log base, or because 2 to the x passes through the order pair 1, 2, log base 2 of x must pass through the order pair 2, 1. And because it passed the graph of the original 2 to the x passes through the order pair -1, 1/2, then our log base 2 of x must pass through the order pair 1/2, -1. And so now I can try to roughly sketch the graph of 2 to the x, or excuse me, the graph of log base 2 of x here, the inverse of 2 to the x. Okay? I'll point out that just like 2 to the x had a horizontal asymptote at y = 0, the graph of log base 2 of x, and indeed all log functions prior to transformations, have vertical asymptotes at x = 0. Okay, so now let's go ahead and look at g inverse of x, which would be equal to the log base 3 of x. So it's going to pass through the order pair 1, 0. Now that doesn't roll off the tongue, but log base anything of 1 is equal to 0. That's the same as the fact anything to the 0th power is 1. Let's go ahead and plot some other points. Well, we know that the 3 to the x function must pass through the order pair 1, 3, and so this must pass through the order pair 3, 1. Log base 3 of 3 must equal 1 by the domain range relationship between a function and its inverse. So there's the order pair 3, 1. Likewise, this is the order pair -1, 1/3 on the graph of 3 to the x, and so the graph of log base 3 of x must pass through the order pair, a little hard to write there, that's the order pair 1/3, -1, and that's just swapping the domain range values. So now I can go ahead and sketch the graph of the log base 3 of x. And indeed, at this point, you should start to have memorized that as long as my base is bigger than 1, the exponential function will look like this, a to the x, and its corresponding log function will look like this, log base a of x. This is for a greater than 1. This generic shape holds for all these log functions as long as the base is bigger than 1. So now let's go ahead and sketch the graph of h of x equals e to the x. Let's go sketch its inverse function. So its inverse function, h inverse of x, you would think maybe to write it as log base e of x, but by convention we write that natural log of x. So again, if you thought that should have been log base e of x, I don't disagree with you. It's just that we choose to use this notation instead. So just like the other two log functions, the log base anything of 1 is 0, so the natural log of 1 is 0. Similarly, because this exponential function passes through the order pair 1, e, its inverse must pass through the order pair e, 1. So there's the order pair e, 1. Now, this is a little bit harder to see, but you should see just like all three of these points have the same x-coordinate, all three of these points right here should have the same y-coordinate. And then I can go ahead and sketch the graph of the natural log of x between the two. So I'm pointing this out because in the past I've had students say, I can sketch the graph of log base 2 of x, or at least I can do that with a table of values, but I really struggle with graphing natural log of x. And I want to point out that their graphs are very similar. Indeed, if you don't put any tick marks on there, you can't really tell the difference between the two graphs. Keeping in mind that all exponential functions prior to transformations pass through the order pair 0, 1. They have a horizontal asymptote at y = 0, and they make this general exponential growth shape. Similarly, all log functions must pass through the order pair 1, 0. They all must have a vertical asymptote at x = 0, and they all must have this similar log shape right here. Okay, the last thing I want to do, folks, is I just want to introduce this topic here of our transformations of our log functions. So I'm asking you in this problem to sketch the graph of natural log of x minus 2 plus 3. Well, this requires me to have a basic understanding of my natural log graph, but there it is. There's the graph of natural log of x. So I'm going to highlight that it must pass through the ordered pair 1, 0, and it has to have a vertical asymptote at x equals 0. So now we're going to do the innermost transformation, this -2. And as a reminder, this -2 shifts the graph of f to the right 2 units. So everything gets moved to the right 2 units, including my vertical asymptote that was at x equals 0. It's now at x equals 2. Similarly, this point right here, which was at the ordered pair 1, 0, the log base anything of 1 is 0. And so this point gets moved to the right 2 units under this transformation. So we're now at the ordered pair 3, 1. And now we can just go ahead and sketch the general log shape. And now we've sketched the graph of the natural log of x minus 2. So we used our base knowledge of the natural log of x. And then we used our understanding of our transformations when I have an x minus a inside the argument of the function. It took the graph of the base function and shifted it to the right 2 units. The last thing we need to do is we need to take into account this +3 outside the argument of the function, but that simply shifts all of the y values up 3 units. So that's not going to affect the vertical asymptote, which was at x equals 2, and it will remain at x equals 2. But this point right here, I'm going to add 3 to all of the y coordinates on my graph. So specifically, this point, which was at 3, 1, prior to this +3 transformation, will now be at the ordered pair 3, 4. So we would place that, and here I'll just kind of fudge that, and there's the ordered pair 3, 4. Now I just recopy that generic shape of the log function, and there's the graph of f of x equals the natural log of x minus 2 plus 3. One more to go. Let's look at the graph of 5 to the x minus 2 plus 3. So this is going to work very similar. It assumes that we know the basic shape of our library function a to the x. So here is the graph of a generic exponential function, and it works for our 5 to the x. This is the ordered pair 0, 1, because all exponential functions prior to their transformations pass through that ordered pair. Likewise, all exponential functions prior to transformations have a horizontal asymptote at y equals 0. Excuse me. So now we go ahead and just simply do our transformations. Here I've got an x minus 2 inside the argument of the function. That's going to take the graph and shift it to the right 2 units. Everything gets moved to the right 2 units. Notice that doesn't affect the location of the horizontal asymptote, but it does affect the location of this point right here that was at 0, 1, and now it's at the ordered pair 2, 1. And then I just simply recopy the generic shape of my exponential function. This is now 5 to the x minus 2. So how do I graph my transformations of log function or exponential functions? I have to know this basic exponential shape, and then I can proceed. The last transformation we need to take into account is this +3, but that's just going to have the effect of shifting this point right here up 3 units. It's going to add 3 to all of the output values of the function. So all the y values get shifted up 3 units. So that, along with everything else, gets shifted up 3 units. So the horizontal asymptote that was at y equals 0 is now at y equals 3. And the ordered pair that was at 2, 1 is now at the ordered pair 2, 4. And then I just simply recopy that generic exponential function shape, and there is the graph of g of x equals 5 to the x minus 2 plus 3. So I use my knowledge of the base exponential function, and then I use my knowledge of transformations to sketch this graph. Folks, we'll get more practice with this in class, but I wanted to get you ready to seeing these transformations so that they're not unfamiliar once we get started. Thanks for your patience, folks. I'll see you next time.